SCSI driver called IO complete request. The class driver can say, I want to know about that under the following conditions. I want to know if it was successful, I want to know if it was an error, or I want to know whether it was canceled. Or I don't want to know at all. Right? If it was successful, hey, maybe what you want to do is just, this guy doesn't even care. Right? Hey, that thing finished, great, I don't care. So then what happens is we then bump the stack pointer up, and we call the file system. Note that these guys don't call IO complete requests. They just get notified along the way that, oh gee, something happened here, right? Now if the class driver had taken this request, this request right here, and sent it down and gotten some piece of it done, when it might want to take the same packet and turn it around and send it back down again. So he's going to have a completion routine. When the completion routine gets called, he's going to tell the IO system, hey, don't call any more completion routines. I want to do some more processing here. Okay, so we stop, and then he gets control, and he takes the packet, puts new parameters in here, and sends it right back down. Okay, so some of these guys have completion routines. We also have power fail routines. This system that we're building is exactly like some of the other systems that we've built in the past, where you can be sitting there and you can be typing along, do, and right in the middle of you typing, boom, you get a brownout, and the system goes down, and when the power comes back on, it comes back up, and you just continue typing right where you left off. Okay, and the way we do that is from the time that AC low begins to go low and the time that DC low actually comes along is several milliseconds. And during that several milliseconds, what we do is we take all the volatile register state in the machine and we save it away in something called a restart parameter block in memory. Okay? And then we go at highest IRQL and we do a self-branch instruction. Okay? And then the power goes, this is provided you have battery backup memory, right? Okay. When the system comes back up and we go to boot, we go out in this RPB and we look at it and we go do a checksum on it. We go, hey, this thing's valid to start with, right? So we take everything and we load it. We get all that state and we load it back into the general purpose registers and et cetera, and then we just continue wherever we left off, right? Just before we continue, however, what we do is we queue a DPC in the system and we call all of the power notification routines for all the device drivers or anybody else who's registered one of these things, and we say, hey, by the way, the power failed. What the device driver does is it goes out and it looks at its device queue or whatever it needs to do to figure out what it was doing at the time, goes out, reinitializes its device, and restarts that request. And it's as if nothing ever happened. Okay?
How big should be the non-volatile?
Excuse me?
How big should be the non-volatile memory? Not to restart exactly when you were.
All of memory.
All of memory.
Yeah, you just back up all of memory, right? Right. Let's see. What are other pieces?
You mean this is a requirement?
No, it's not a requirement. It's a feature.
No. But in order to survive fire failure, you can potentially embed a system where one of your, certain area of your memory is not backed up without the whole thing.
Well, what part would you like to not have backed up? The user's page that contained the,
all new text.
The stuff that you were just typing, or would you like to have the piece of memory that contained, your salary increase in it? I mean, what do you choose, right?
I want to predict on this which one is relevant.
Oh, digital's not that bad. I mean, I used to work for DEC. I worked for DEC for 13 years. Let's see what else is in here.
That's not a requirement for being part of this project, though.
Sorry?
So that's not a requirement for being part of this project.
Just for you, because we like it. Error log routines. Let's see if I can find a picture here and make sure I got them all. Pull out my old presentation.
By the way, you don't necessarily have to back up like your memory for hours or anything like that. I mean, most power fails are for like short periods of time, so you don't.
Yeah, I mean, this is like 10 minutes, right? If you want more than that, then you use UPC or UPS, UPC.
This little barcode can receive all evils.
Right. Oh, right, and the unload routine. I knew there was something else I was forgetting. Our drivers are dynamically loadable and unloadable. right? So if at any time during the system you decide that, well, gee whiz, I got this new update for this driver, so what I'll do is I'll unload the current driver and put in a new copy. You can do that.
What was the one before last?
Error log, just little error log routines that go out, and log errors.
Just want to check this to make sure I've got this right. The kernel, when you have a kernel process that, a fully blown process that runs in kernel mode, it uses the user virtual address space as its cache, right? Is that what you said?
I said you could use it for its cache. It turns out that our I/O system, our I/O system's pretty cool the way it caches. It actually uses memory management to do its caches, and it uses sections and mapped memory. When you go out and you open a file, when you call the file system, you say, I'd like to open this file. The file system says, okay, great. And then the first time you try and touch it, it calls the cache manager, and the cache manager calls memory management and says, I would like to create a section that represents this file. And then when you want to read or write data, it simply maps various pieces of that into the virtual address space of the system, and then it touches it.
So it maps a window onto the file.
Maps a window onto the file, and then it just touches it. And of course, if it's not there, it causes a page fault. And the pager calls the I/O system and says, please go read this page, who calls the file system and says, please go read this page, and the file system says, okay, and it goes and it reads it. Okay, so what you have in memory in the cache at any given time is based on what you've been doing, because what you're not touching eventually gets bubbled up to, hi there, this thing is the least recently used thing, and it gets kicked out of your working set and it goes out to the paging file, where it goes out to whatever file it came from originally, right? It turns out that one of the nice things about this is if the user decides, hey, the way I'd like to read and write this file is, once I open it, I'll create a section, and oh, by the way, the section pointer he gets is the exact same one that the cache manager is using, right? And then he says, okay, I'd like to map some of this into my virtual address space, and now, if this guy over here says nt write file into this file, and we put it in there, if the user who has the same section open happen to have that same block map, he can get it by simply moving it out of memory. Okay, other questions? Yes.
When you were dealing with your very willing floppy, how did you know that the thing finally timed out? Did you have a real-time clock something?
Yeah, I mean, what the thing does is, the loop for this thing inside the code is, when it goes to get one of these bytes, or it goes to put one of these bytes, the code says, for I equals 1 to 25, try it, and if it doesn't work, then wait for 10 milliseconds. Okay, note, however, that in real time, here's a click for 10 milliseconds, and here's a click for 10 milliseconds, and you may have asked right there, so you aren't guaranteed that you've done that, right?
That's an important number.
Right.
So he said you did it twice.
Right, so then what I do is I put this whole thing in a for I equals 1 to 2 loop, and if it still doesn't get it, then when I come out, I decide that that's a timeout.
So you don't have any ability to, asynchronously start your 10 millisecond time?
Yeah, saying wait for 10 milliseconds says...
You said wait with your little carrot there, right in front of the timer.
Right, you're just not guaranteed that you're going to wait for that.
Wait 10 milliseconds is in fact, in use terminology, would be wait for next lightning bolt.
That's right. That's right. Absolutely. Okay, the other thing is the I/O system provides driver writers with I/O timers, and they have a 1 second interval. And so basically what happens is the driver writer goes out and he says, okay, I've got 5 seconds to do this operation, and he sets a counter equal to, say, 5. Okay, and then whenever its routine gets called, I call the driver once every second, and he goes out and he looks and he says, is the count positive? Yeah, decrement it, did it go to 0? Right, and if you put a -1 in it, by convention, that means, we're not timing anything, just go away. Right. Same thing VMS does. VMS does exactly the same thing. In some senses, some of these things are VMS-like, for those of you that work for DEC. An IRP is an IRP, except that ours don't look anything like Right, that's right. And you can think of this as the FDT, but it's not really. It's those kinds of things.
Well, you turned all this stuff into objects, basically.
We took some of this stuff and we turned it into objects, yeah. I mean, this thing is a UCB, except that we dynamically define what the extensions look like and stuff like that, right? Some of the things, the stack locations and really the very regular and strict layering rules is something that is totally new. This is something that we've come up with over a period of years of working on other things, both after VMS or after RSX in that case. Okay, any other questions?
Assume you're writing a device driver for keyboard and mouse. Where do you find the specifications for the particular I/O controls that you need to provide?
There are in the system files of the form NT device driver and then device driver type.h, and all the IOCTLs for every particular device type is there. So you'd see KBD, MOU, disk, net, you know,
Okay,
etc.
and you presumably using this to enforce standard IOCTLs, so that if I have two different mice, I won't have two different IOCTLs do the same thing.
That's right. That's right. And we've gone all the way to the point of good Lord.
I'm assuming you don't have a source license for your team that you're not selling yet. Do you need a regular document that has some of this somewhere, or?
Before we ship, I mean, if you've seen the NT workbook, in the back of either the I/O spec or the driver spec, there are two appendices. One defines all the IOCTLs for all the drivers, and the other one contains all the file system controls for all the file systems.
What we provide is, in general, we provide, in addition to the regular operating system the end users provide, we provide a software developer's kit that has all the header files, etc., that the average application developer would want to see. Then we provide another kit called device driver writer's kit that would have in it all the information like these files, etc., and documentation you need to write device drivers.
Right.
And then you thirdly have source licenses. So we do business, because we're more commercially oriented, buy things at different levels without having to buy the shrink wrap box. You can buy a software development kit, you can buy a device driver development kit, and then you can take out source licenses. But you don't have, it's not like Unix where it's binary one or the other.
So, and this is in the back of these black binders that we're receiving today, right?
Yeah, you guys are fully in the food queue here. You're getting unchewed stuff.
Yeah, in fact, what you'll see is if you look in both of those appendices, they all start with. Right.
So the ones that we're getting today have PBS in it.
That's right.
So we can't get a listing in the .h files.
You can get a list of .h files.
There you go. Can you just
Well,
start?
it helps the guy who's working on that keyboard mouse driver to get
In
all
your case, if you want to start doing something, we'll give you everything you need.
I'm not allowed to say that, but he is. If you look at the IOCTLs too, the other thing that you'll notice is that the upper part of the IOCTLs, the control codes themselves are 32 bits, and the upper 16 bits are really the device type, where that bit is reserved for customers, and then the low order bit the low order 16 bit is really the function, where that bit is defined or is reserved for customers, except that there are a couple of bits that we've pulled out. In fact, there are several bits that we've pulled out. These two guys, when I make an NT device I/O control file or an NTFS control file call, and I give an input buffer, an output buffer, and then I give one of these function codes, and the two bits 1 and 0, have tell the I/O system how the driver would like to see those two particular buffers passed to it based on the control code. Okay? In this particular case, it says I would like you to generate an intermediate system buffer, copy the input data into it, and then call me. And when I'm all done, I will have put the data that I'm returning into that intermediate system buffer, and the I/O system, upon completion of the request, automatically copies that back into the user's address space and deallocates the buffer, okay? 0, 1 says, I'd like to see this one, I'd like to see the input buffer buffered, and I'd like to see the output buffer locked down and have an MDL describing it. And then, you know, there's various combinations. This one says, I'd like to do everything by myself, okay? These 2 bits are an access check type that tell me what kind of access that the user must have to his handle in order to be calling this code in the first place, so I can call a security manager and find out whether it's okay. One of the things that I didn't mention along this buffered I/O and direct I/O and stuff like that is inside the device object are some flags, and one of the flags says whether or not you do buffered I/O, one of them says whether or not you do direct I/O. If you set the one that says buffered, anytime someone calls me and I'm going to give some data to you, or I'm going to get some data from you, I will go off into system space and I will allocate out a non-page pool a buffer, an intermediary buffer, which I'll take the data and put it in so that you can safely get it out in the context of another thread, like the floppy thread, for example. Or you can put data in there and then I'll automatically put it back into the user's address space upon completion. Direct I/O says that what you want to do is you want to see an MDL, that's a memory descriptor list, built for the user's buffer, which is locked down. So I lock it down and then I build a memory descriptor list for it. And you can use that memory descriptor list later down here in one of these adapters and call the I/O system and say, hey, here's an MDL. Go do whatever you got to do to whatever kind of mapping registers happen to be out there, depending on what kind of processor I'm on, and I'll go do that for you. So that you can then just tell the device, hey, go, right? And all the mapping automatically occurs for you. And if you don't set either one of them, which is what our file systems do, then I won't do either, and I'll give you all the right pointers. And then while you're in that user's context, you can do all your own probing or wrapping your things around exception handlers and just copying data. For example, our file systems say, I don't want to do either one, because what happens is when the file system gets called, if this is a read, for example, it wants to call the cache manager and say, hey, I would like to read some data out of the cache into that buffer right there, right? And the cache manager inside of a try except exception handler simply says, copy the data, right? And when it goes to touch the first byte, if it gets a page fault, then we go through all the memory management and everything until we get that page into memory. And then we resume right where we left off, and he just copies the data straight into the user's buffer. So there's no intermediary buffering. We didn't do any locking down of pages or anything.
Okay, you guys are punch drunk at this point?
We're having a good time.
Having a good time.
Anybody who can do all this and talk to a floppy. Undying admiration.
I have one more vocabulary question.
Okay.
From one of your writings that I read yesterday on the plane. What's transmogrification?
Transmogrification?
Aside from Calvin and Hobbes.
Sorry?
Forgot to find something.
What does it mean to
Something to do
transmogrify
with horror movies. You know?
Transmogrification is taking something and porting it to something else or manipulating it slightly to make it into something else.
Dr. Jekyll and Mr. Hyde.
Right, it'll happen to him in 7 years when he gets to be a manager.
When you had two Frenchmen reading that in the plane last night.
Right, like we took a Pascal compiler once and we transmogrified the parser by making minor modifications here and there to parse a different language, for example.
It's forcing a round peg into a square hole.
There you go. That's how a VP says it. But it's exactly right. That's a perfect example. That's a perfect example. Okay.
Are there any, just at a high level, before we break up, any high level issues, questions, concerns that came up that I could pick up on?
You said we could have anything we wanted from you. I'd like your card.
Maybe more difficult than you realize.